Welcome to Lecture 39. This will be our last lecture of the semester, and this will just be a brief review of tests 33 and 36. In 33, we were talking about the Deutsch-Joshua algorithm, and in 36, we were talking about the Bernstein-Vazirani algorithm. And here for this, the first few lines here, down to this point, I have copied exactly some material from Lecture 33 because it applies to both Test 33 and 36. So for both of these algorithms, the normal starting state C0 is given by this. We have n zeros, the first n qubits are all 0, and then the last qubit is 1. And you will recall that in tests 33 and 36, we also considered what would happen if we had different starting states. Namely, we considered what would happen if we had the first, in every one of the options that we considered, in every single one of them, just as is the case in here. In every single case, the first n qubits are 0, but what we did was to consider the effect of varying this last qubit. And the normal value for the last qubit is 1, but in tests 33 and 36, we considered what would happen if we made the last qubit equal to 0 or plus or minus. And I want to discuss that in some little bit of detail here. But let's begin with a review of what happens in the usual case when we start with 1. So C0 here, again, is n zeros, and then the last qubit is 1. And we apply H to each one of these n plus 1 qubits. And so here we have W applied to those first n qubits, and remember that W is simply H, the tensor product of H with itself n times, and then the last H is applied to the 1, and so then coming from here to here, we just keep the first part, but we can go ahead and evaluate immediately H acting on 1, and it's equal to 0 minus 1 over square root of 2. And then coming down to the next line, we know from some work we did previously that W acting on this these n qubits that are all equal to 0 will give us this 1 over square root of 2 to the n times the sum over x equals any element of the standard basis for n qubit states of x, and then we just bring down this last part, 0 minus 1 over the square root of 2. Now and this is what we're calling C1. After we've operated on each qubit of C0 with H, we get C1, which is right here. And then this C1 enters the unitary transformation use of F, and then we get this output. And we're going to consider the first n qubits to be X, the last qubit is Y, and the way that this will work is then for the outputs, the first n qubits will be X, and the last qubit will be Y exclusive ORed with f of x, where f is some function. And right now we're not going to worry too much about what that function is. We're just saying that we have y exclusive OR f of x. And so in the case that we have here, C1, where the last qubit was 1 in C0, so this is the normal case, and we get this C1, then in that case y is equal to 0 minus 1 over square root of 2. And so we've noted that right over here, y equals 0 minus 1 over the square root of 2. And then we asked ourselves, what is y exclusive OR f of x in this case? And we found out that, well, let's see, let's follow the reasoning here. If we have 0 exclusive or f of x, then this would give us f of x. But 1 exclusive or with f of x will give us the complement of f of x. And the notation here, I should have had this on the end. Okay, so we have this right here is equal to this y exclusive ORed with f of x. We get f of x minus f prime of x over the square root of 2. Oh, I see. Somehow this has gotten garbled here a little bit. Let's see if I can make this a little clearer. Somehow in copying this over, this got garbled. So let me clear this up. I believe I'll just erase this. This is a topic that we've talked about before, so I'll just put it like this: 0 exclusive or f of x is equal to f of x, and 1 exclusive or f of x is f prime of x, and so that's how we get this value right here for y exclusive or f of x. And then when we think about, and once again it looks like the copying didn't go quite well here either, this should be x. Okay, but now when we look at this f of x minus f prime of x over the square root of 2, well, if f of x, now if f of x is equal to 0, then this would be 0 minus 1 over the square root of 2. But if f of x is equal to 1, then this would be 1 minus 0 over the square root of 2. And so we can write both of those results in 1 by writing it as negative 1 to the f of x power times 0 minus 1 over square root of 2, because when f of x is equal to 0, this is indeed equal to 0 minus 1 over square root of 2, and when f of x is equal to 1, it is indeed equal to 1 minus 0 over the square root of 2, because when f of x is equal to 1, this would be negative 1 to the 1 power, so it would be negative 1, and that would flip the numerator to make it 1 minus 0 of the square root of 2. So this is what we obtain for that last qubit when we start with the normal starting state on either the Deutsch-Joshua or the Bernstein-Vazirani algorithm. And so then we take this and we can plug that into C3, which is the result that we get here. As you can see, let's see, I'm sorry, plug it into C2, because C2 is the output from the unitary transformation when C1 is the input. And so you can see here that we have the negative 1 to the f of x and the 0 minus 1 over square root of 2. So we've brought that over here for C2, and the rest of C2 is just bringing down C1, because remember that the first n qubits of C2 match the first n qubits of C1. So that's why this first bit of C2 is exactly the same as the first part of C1, but the last bit, or last part has been changed. Instead of 0 minus 1 over square root of 2, we now have this negative 1 to the f of x times 0 minus 1 over the square root of 2. So this is the value that we would get for C2 under normal circumstances. And now we want to understand what happens to this C2, and we also want to understand what C2 would be for the alternate cases that we want to consider. Okay, well, when we look at this C2 here, and ask, how does Alice use this to determine if f is constant or balanced? Well, what she will do is she will apply h to each of the first n qubits of this to get this expression right here. We remember h applied n times is just w, so we have this w acting on the x, but everything else is exactly the same. We have 1 over square root of 2 to the n comes down, negative 1 to the f of x comes down, 0 minus 1 over square root of 2 comes down. So the only thing we've done here in going from C2 to C3 is to let h act on each one of those first n qubits. In other words, it acts on x. So we have w acting on x. And from a result that we obtained earlier, we know that that can be written like this: negative 1 to the x dot z times z, and we have 1 over square root of 2n, and here z is any element of the standard basis for n qubit states. And we can take this 1 over square root of, again, this is a previous result that you can see in some of our previous lectures. So this 1 over square root of 2 to the n combines with this 1 over square root of 2 to the n to give 1 over 2 to the n, and then we have these two summations. Both of them are over any element of the standard basis for n qubit states, and then when we combine the negative 1 to the x dot z with the negative 1 to the f of x, we get negative 1 to the x dot z plus f of x, and then the z, and then this last qubit, 0 minus 1 over square root of 2. And that's the end of what we have brought over now from lecture 33. So before we discuss that any further, let's now see what C3 would be for the other cases. So we will note that this is C3 when C0 is equal to zero. We have n zeros and 1. Okay? And so now we ask what? Before we go any further with that C3, let's go ahead and find out what C3 will be for the other cases. What will C3 be for the other 3 cases? And by that we mean we can say 1 will be actually I'm going to maybe do it like this. We'll treat 1 as the case that we've already done. C0 equals 0. We have n zeros and then 1. That will be case 1. And so by the other 3 cases, I'll mean 2, 3, and 4. So in the second case that we want to look at, we'll have that. In the third case, we will have this. And in the fourth case, we will have that. So let's just go through this, and I believe by referring to what we did in the first case, we'll be able to easily answer these questions. So remember, to get C1 from C0, as we've already said, we just operate on every single qubit with H. And when we do that for case 1, this is what we're going to get. So what do we get in the other cases? So for let's say it like this. C1 equals, and again we'll do case 1, case 2, case 3, and case 4. Now in case 1, we had 1 over square root of 2 to the n times the summation over x, and remember, this is x is any element of the standard basis here for n-qubit states, so I'm just going to write it as x because we understand what that is now. So we have x, and then remember that the last part of C1 here is h acting on that final qubit of C0. And we know that h acting on 1 is 0 minus 1 over the square root of 2. So we have 0 minus 1 over square root of 2. Now, C2, C1 for case 2 is when we start out with this value of C0 here. So the first part is going to be exactly the same, and I'll just put ditto marks there. But then when h acts on 0, we will get 0 plus 1 over the square root of 2 for that one. Again, this is h acting on this 1 here, and this is h acting on the 0 in case 2. In case 3, the first part will also be the same, but now h acting on plus just gives us 0 for the last qubit. And then finally for case 4, again the first part is the same, but h acting on minus will be 1. So here will be the value that we will get for C1 in each of the 4 cases. Now let's refresh our memory about how we got C2 from C1. And remember that that's by we feed C1 into the unitary transformation to get C2. And remember that then we know the first n qubits will be the same. It's just that last qubit that will be changed. So let's come down here and see what we get then in all 4 cases. So C2 equals, okay, in case 1, it was the first part remains the same. The first n qubits remain the same. So we have 1 over square root of 2 to the n, sum over x, and then x. And then remember that we're going to treat this last part as y, and so we get y exclusive or f of x as the last qubit. Remember, just as we talked about right up here over in the right hand margin, y exclusive or f of x, which can finally be simplified to negative 1 to the f of x power times 0 minus 1 over the square root of 2. So negative 1 to the f of x power times 0 minus 1 over square root of 2. That's what we get in case 1. Now, in case 2, again, the first n qubits are the same. So I'll put ditto marks here. But now we have to, for case 2, we have to figure out what happens when y is equal to 0 plus 1 over the square root of 2. So we're asking for case 2, okay, we'll put it like this. For case 2, y, that's the last qubit, y is equal to 0 plus 1 over the square root of 2. So what is y exclusive or f of x in this case? Well, we know that 0 exclusive or f of x would be f of x. And as we saw above, 1 exclusive or f of x will be the complement of f of x, or f prime of x. So we would get f of x plus f prime of x over the square root of 2 in this case. And regardless of whether f of x is 0 or f of x is 1, this will turn out to be simply 0 plus 1 over the square root of 2. There's no negative 1 to the f of x power multiplying that. It's just 0 plus 1 over the square root of 2. So in this case then, in case 2, C2 will be given by that. The first part, the 1 over square root of 2 to the n, and the summation of x over x of x, that part is the same, but the negative 1 to the f of x times 0 minus 1 over square root of 2 is simply replaced in case 2 by 0 plus 1 over square root of 2. What about in case 3? Well, in case 3 again, the first part is the same. But now we need to figure out when we have 0 as the last qubit. Okay, now we can say for case 3, y equals 0. So y exclusive or f of x in this case will simply be equal to f of x. Because y is 0, and 0 exclusive ORed with something is that something. And so for this one, number 3 would get that. And then by the same kind of reasoning for case 4, we would get f prime of x, because 1 exclusive or f of x is f prime of x. So these are the values that we would get for C2 in each of our 4 cases. And so now let's think about C3. Okay, again, let's go and review how we got C3 from C2. And the answer was that we let H act on each of the first n qubits of C2 to obtain C3. So let's see what happens when we do that with each of the cases. Here in the original case, this is what we're going to get right here. So let's look in this case and all the others as well. Okay, so we get 1 over 2 to the n, sum over x, sum over z of negative 1 to the x dot z plus f of x z, and then we carry along. Remember, we didn't to get C3 from C2, we only operate on the first n qubits. We don't bother that last qubit. So we get 0 minus 1. We just bring this down, 0 minus 1 over square root of 2. Now for case 2, when our C2 is equal to this, rather than what we had there in case 1, then we'll just get 1 over 2 to the n, sum over x, sum over z, negative 1 to the x dot z. But remember now, we don't have any negative 1 to the f of x here, so we don't have an f of x in the exponent for this one. And then we'll get z, and bringing down the last qubit, 0 plus 1 over square root of 2. Now, what about case 3? Well, in case 3, we will get 1 over 2 to the n, sum over x, sum over z, negative 1 to the x dot z, and then z, and bring down our f of x. And then finally, for case 4, 1 over 2 to the n, sum over x, sum over z, negative 1 to the x dot z, z, and f prime of x. And so now we have C3 for each of our 4 cases. Now it's important to remember for these 4 expressions for C3, it's important to remember that this is valid for both the Deutsch-Joschka and the Bernstein-Vazirani algorithm, because the first steps in both of these algorithms are the same. In fact, really all the steps are the same. It's just a different interpretation and a different function that we're using. So these 4 expressions are good for both algorithms. And in both algorithms, we know that the next step after we have C3 is to measure the first n qubits. But the trick here is to figure out what that measurement will yield. And the easiest case here to consider is case 2. So let's just say, to understand what will happen when the first n qubits are measured with the standard basis, first consider case 2, because as you can easily see from these expressions, case 2 is actually the one that yields the simplest expression for C3. So in case 2, we have that C3 is equal to 1 over 2 to the n, sum over x, sum over z, negative 1 to the x dot z, z, and then 0 plus 1 over the square root of 2. Now, the easiest way to see what this is equal to is to do the following. Let's switch the order of the summations. So we have sum over z, sum over x, negative 1 to the x dot z, and z, 0 plus 1 over square root of 2. And if you wish, you could even take this z cat here over here to this space between the two summation signs, because it does not depend on x. But the important thing here is to look at this summation over x of negative 1 to the x dot z. We have learned from one of our previous discussions, one of our previous results, that negative 1 to the x dot z, when you sum over all the x's, where x is any element of the standard basis for n-qubit states, and z is some particular n-qubit state. Notice that we're going to sum over all of them, but we just consider them one at a time, because this is the summation here on the outside. So we'll consider, in other words, we'll fetch one value of z and do the sum, and then we'll get the next value of z and do the sum, and the next value of z and do the sum. So we're just using one value of z at a time. And as we were saying, then that this sum is actually for any value of z, this summation here will be equal to 0, except when z is the qubit consisting of the n-qubit state consisting of all zeros. And in that case, of course, if it's all zeros, then x dot z is 0, and negative 1 to the 0 is 1. So we have the summation of 1 over these 2 to the n states, so we would get 2 to the n in that case. So, but all of this discussion that we just made, in all this discussion, it was crucial that we could treat just this part, just this little summation right here. We could treat that separately from everything else. And we could do that because this z depended only on the z summation, and this last term here is a constant, so it's completely independent of both the z and the x summations. So what we conclude then here is that this is equal to 1 over 2 to the n, and then as we said, when we pick our different z's, for every z we pick, this summation is going to be 0, except for when z is the state consisting of or the n-qubit state consisting of all zeros. In that case is equal to 2 to the n. So we get 2 to the n times 0, the n0 state there, and then 0 plus 1 over square root of 2. And of course the 2 to the n and 1 over 2 to the n cancel, and so we would get this. So our conclusion is that in case 2, C3 is the same as this, and again, let's make sure to state this is for case 2. So this is C3 for case 2, and so very obviously it doesn't matter what f is equal to. Measurement of the first n qubits with the standard basis will definitely yield the n0 state. But once again, I want to just really emphasize that in this derivation of that result, it was crucial that this summation was independent of everything else. So now let's look at the second most challenging case, which is case 1. Now in case 1, which of course is the normal case, we have 1 over 2 to the n, sum over x, sum over z, negative 1 to the x dot z plus f of x, z, and 0 minus 1 over square root of 2. Now again, if we wish, we could reverse the order of the summations, make this sum over z, sum over x, negative 1 to the x dot z plus f of x, z, 0 minus 1 over square root of 2. Now, let's think for a moment about the Deutsch-Joschel algorithm. Okay? And remember, in the Deutsch-Joschel algorithm, we have two choices for f of x. It can either be constant or it can be balanced. So let's just say if... Now again, I want to, before I go any further, I want to emphasize, remember in case 2 that we just looked at, we never had to consider f of x at all. The result that we derived was good for any f of x. But to make more headway on this expression for case 1, we have to consider what f of x is equal to. So let's say if f of x is constant. Okay, we'll just, then if f of x is equal to constant, then we'll just suppose f of x equals k. We'll let that constant be k, and of course k is then going to be equal to either 0 or 1, but the important thing is that it will be a constant. Well, in this case, call this a, maybe 1a, then in this case, we would have C3 equals, well, the negative 1 to the f of x part here will become negative 1 to the k, and we can just bring that out. So we'll have negative 1 to the k power over 2 to the n, sum over z, sum over x, negative 1 to the x dot z, z, 0 minus 1 over square root of 2. And now we're back in exactly the same kind of situation that we were in the previous case we discussed, because this part now is going to be separate from everything else, is independent of it. And so we can say then that C3 in this case will be equal to negative 1 to the k power over 2 to the n times 2 to the n, 0, and then 0 minus 1 over square root of 2. So this is in case 1 and f of x equals constant k. This is what we would get. And once again, you can see in this case, of course the 2 to the n's will cancel out. Negative 1 to the k is either going to be equal to negative 1 or positive 1, but still a measurement of the first n qubits will yield n zeros. That's if f of x is constant. Now, but once again, let me emphasize, the thing that allows us, the observation that allows us to make this observation, to get this final expression, is the observation that this part here does not depend on anything, or nothing else depends on this summation. There's nothing else, there's no more x's anywhere else that have to be taken into account in this summation, so it can be done separately to give us 2 to the n times this all zero qubit, or all zero state. And so that's what allows us to make progress. Okay, now if f of x is balanced, okay, so we need to go back up now to this expression right here. So we have C3 equals 1 over 2 to the n sum over z sum over x negative 1 to the x dot z plus f of x z 0 minus 1 over square root of 2. And how do we reason through this one? Well, we can say that this is equal to, we can break up the sum over z. We'll say, we'll do it like this. We'll have a sum, but it's not really a sum because it's only going to be one term. So we'll have z equals 0. Actually, let me write this to make sure it's clear. I mean z equals, well, by 0 I mean the, I mean that, n zeros, of course. Okay, so, there. Okay, so we've taken one term out of this sum, the z equals 0, and then we will also have to take all the other terms. So 1 over 2 to the n sum z not equal to 0. Okay, so let me make sure everybody's following here. I've just broken up this outer sum into two parts. One part is this sum when z is equal to 0, so that's just one term of that sum. And the other is when z is not equal to 0, so that's the other 2 to the n minus 1 terms in the standard basis for n-qubit states. So I've just decided to break it up like this. Now, if we proceed with that, okay, the first one, since we know that z is equal to 0, in that case it becomes a little easier, because when z is equal to 0, then x dot z is 0, and this just becomes negative 1 to the f of x. So, and we don't have to sum over, it's not really a sum, like I say, because there's only one value of z we're considering here. So we have sum over x of negative 1 to the f of x, and remember z is 0, and then we have this, and then of course we have all the rest of it, 1 over 2 to the n sum z not equal to 0, negative 1 to the x dot z plus f of x, z 0 minus 1 over square root of 2. And now if you look at this for a moment, you will see that this does simplify because of the following. Okay, now when we look at this first part of this expression, notice that this summation over f of x is only involves this one term. There's no more x's anywhere else in this term. And since f of x is balanced, negative 1 to the f of x, half the time it'll be negative 1 to the 0, which is 1, and half the time it'll be negative 1 to the 1, which is negative 1. And so, since, like I say, it's balanced, so it'll be exactly half and half, and when we add them all up, what do we get? 0. So this first term will disappear, and we get 1 over 2 to the n sum z not equal to 0, negative 1 to the x dot z plus f of x z and 0 minus 1 over square root of 2. So what can we say in this case? This is case 1. Case 1. No, I'm sorry. This should be not case. This is not. Yes, that's right. This is case 1. That's right. Case 1 and f of x is balanced. And notice that we can now say something about this, which is that if we measure the first n qubits are represented here by this sum, along with 1 over 2 to the n. But the important thing is that we definitely will not get the all zero state out of that. That one is definitely left out. So we will get something other than the all zero state. So that's what we can say will happen. We will definitely measure something other than the all zero state if f of x is balanced. Now, of course, these two cases we've considered, 1a and 1b. Here's 1a and 1b. These both refer to the Deutsch-Joscha algorithm. When we go to the Bernstein-Vazirani algorithm, the analysis will be a little bit different. But again, the crucial point will be the ability to evaluate these summations without concern for this last qubit. And that is perfectly all right, because in both case 1 and in case 2, this last qubit is a constant for all cases, and that's what allows us to be able to switch. We can switch the order of summation anyway, but then after we have switched it, then we can do the interior x summation. We can do it rather easily for cases 1 and 2, because in both of those cases, the last qubit is constant, and therefore it is unentangled from the first n qubits, and we can evaluate that sum directly. But the problem for cases 3 and 4 is that even, again, you can change the order of summation if you wish, but then you cannot proceed to evaluate these summations over x, because the last qubit also depends on x. Or another way of saying that is that in these cases, the last qubit will be entangled with the first n qubits. So for instance, if you look at number 3 and compare it to number 2, they look very similar, but you cannot say, for instance, that you always have 0 for the first n qubits in case 3, because you see, you know, that depends on, in case 2, remember that depended on the fact that for all of the other values of z, that these terms would cancel each other out. But they might not do that when the last qubit is f of x, because that means that the last qubit will sometimes, it could sometimes be 0, and it could sometimes be 1. And for the case when it's 0, perhaps the first n qubits will not add up to 0. And likewise, when the last qubit is 1, the first n qubits do not add up to 0. They would then need to add up to 0 separately rather than taking them all together. And so in cases 3 and 4, it's simply going to be impossible for us to predict with 100% certainty what will happen when we measure the first n qubits with the standard basis. And that is the important point that I wanted you to take away from this lecture. And once again, when that last qubit is constant, then we can evaluate what's going on with the first n qubits. But when the last qubit is not a constant, and instead is entangled with the first n qubits, then we're not going to be able to evaluate these summations and say with complete certainty or what a measurement of the first n qubits with the standard basis would yield. And so that is it. I don't have any questions for this. This was just an elaboration on the material we covered in tests 33 and 36. So that's it, and thanks, and I'll see you soon.